Okay, I think we'll get started. So today we're going to talk about phase equilibria. We're not going to go too deep into this topic. We'll have a lot of discussion of this throughout the full curriculum as we get up to more of our advanced courses. But it is important to catch some of the important concepts that we should know about even in the introductory course. So we're talking about a single homogeneous substance that can go between phases. And we're going to kind of stick to solid, liquid, gas, so sort of normal substances, normal phases. When we're talking about one phase to another, we'll call one phase alpha, one phase beta, and either we're out of equilibrium and we will be moving to one phase to another, but then we'll also talk about in equilibrium. So associated with any homogeneous substance is what's called a phase diagram. And there are a number of different phase diagrams. The most important one for us is going to be the pressure-temperature diagram. And what we do is we draw lines where the chemical potentials are equal. So along this line is the equilibrium between solid and gas. And across, as you cross this line, you will go, say, from solid to gas or from gas to solid. So this represents the sublimation deposition line, and right on the line, we're in equilibrium. This line goes off to infinity, and this is solid to liquid, so that would represent melting and freezing. And then this line terminates here, and it represents the liquid-gas equilibrium, which would be condensation and evaporation. There's a couple of important points. This is called the triple point, where all three of these come together, and that is the one special case where mu solid equals mu liquid equals mu gas. So all three phases are in equilibrium. And then this line actually terminates at what's called a critical point. And what's interesting here is that if we're a solid, to go to a liquid or to a gas, we must have undergone a phase transition. But what's interesting is that if we're a gas and we raise our temperature, raise our pressure, lower our temperature, lower our pressure, we can go all the way from a gas to a solid or a solid to a gas without ever having a phase transition. So that's a consequence of this line terminating here at the critical point. The region at temperatures higher than the critical point and pressures higher than the critical point is called the supercritical region. This region is called the liquid, solid, gas. Okay. All right, well, to go further, we need to back up a little bit and reconnect with the first law of thermodynamics and chemical potential. So I'm just going to state this. This is, I think we're just going to have to take this. We'll see where this comes from much later courses down the line in the curriculum. But just roughly speaking, what we're seeing here is that the total energy is the thermal energy due to making things random or having entropy, and then a pressure volume energy, and then finally a chemical energy. And so when we start with this representation of the total internal energy for the system, what we're really interested in is changes. So let's write the du for this, and we're going to do it just purely mathematically. So the d operation undergoes the product rule. So right over here, dTs is s, d is first, t times ds plus s times dt. And that will be true for all these terms. And so these three terms will end up being 6. Here's the ts term, here's the vp term, and here's the mu n term. Now, we have the first law. So here's the physics. This is conservation of energy. Any change in entropy, here's our PV term, and then here's our chemical term. Now this is just for a single substance, and no, not phase equilibrium yet, but just one single substance that can change the amount of material. Well, given this is the first law, here's just our purely mathematical expression, then what do we notice? We notice this first law in here. So here's this term. Here's this term. And here's this term. And so that leaves this term, and this term. And thus, those must be zero, because this is what du is. Right? Here's just the purely mathematical expression. And so we get this relationship. Now this is going to be important for us, and I know that it might be a little bit unsatisfactory of where we even started, but hopefully, given this, you see where this evolves to. So we can solve for dn, or for d mu, sorry. We solve for d mu, dividing by n. Well, these are, S is extensive. You divide by n, and we get the molar entropy. Likewise, we'll get the molar volume. So we basically put this into intensive variables by dividing out by that n. And we have an expression here now for the chemical potential in terms of entropy and temperature, and volume and pressure. Okay, well now we go to a phase equilibria. So that will be one of these equilibria. Right, we're not going to talk about the triple point. So alpha, beta, could be any solid, liquid, whatever. Now, at equilibrium, it's true that the chemical potentials are equal, right? That's what it means to be in equilibrium. So we're right on one of these lines. Well, I'm going to take now and run the d operator, the differential operator, through this equation and get du equals d mu, and that's true along this line. Well, we've got an expression for the pure individual substances. So this is going to be in phase alpha, right? That's d mu alpha, and here's d mu beta. So we can set these two equal to each other. Now let's collect terms, and we're going to go products minus reactants. So, oh, do I have this? I think I have this backwards. So we'll bring this over to this side, and it'll be products minus reactants. So that should be a positive here. And then we'll bring this over to this side. This will be a minus here. Okay. What do these represent? This symbol here just represents a phase change from alpha to beta. And so we have the change in molar entropy and the change in molar volume in going from alpha to beta. Well, now let's get these factors to one side and the differentials to the other, and write a differential equation. dp equals ds, dp dt equals delta s over delta v. And this is true for any phase transition, and this is called the Clapeyron equation. So let's do an interesting example here. Let's do water. You'll notice it was intentional that I made this line kind of slope this way ever so slightly. It's a very, very steep line, but for most substances it slopes this way, has a positive slope. But water actually has a negative slope. And let's see where that comes from based on the Clapeyron equation. So we're going to set this up so that we're solid we're solid to liquid. So the product minus reactant, we're going from a solid to a liquid. So we expect our entropy to increase, right? We have more disordered system in the liquid than the water. So greater entropy for liquid than solid. We're as written, we would be liquid minus solid. So that would be positive. Now let's check the volume here. Solid goes to liquid. We actually have a decrease in volume. This is unusual. Water's unique in this way. Other substances, the solid is more dense than the liquid, and the solid sinks to the bottom of its own liquid. But water is, as you well know, ice floats. So the solid is less dense, and so the same amount of water molecules in a solid will take up more volume than in a liquid. And so liquid minus solid is negative. And so if we look at this side, we have a positive over a negative. We should have a negative dP dt. Well, what is dP dt? That's the slope. This is pressure temperature. That's the slope of this line, right? That is the way P changes with T, the slope of that line. And so we get a negative slope, just as expected for water. And water, again, is unique in that regard. Okay, well, what are these referred to as? These are referred to as the latent properties. So let's write our one of our delta G equations. That's, oops, got a mistake here. That relates delta G to enthalpy and to entropy. Oh, gosh, two mistakes. There we go. Delta G equals delta H minus T delta S. So that's our equation. This is called latent free energy. This is called latent enthalpy. It's also called latent heat because, as we know, under reversible and constant pressure conditions, enthalpy is heat. And then this is called latent entropy. Well, let's plot heat added to a system versus temperature of that system for a standard material. And let's go from really cold. So really cold, we're going to be solid. Let's just, you can just have water in mind if you want. So we've got solid. As we add heat, we're going to raise the temperature of that solid. So adding heat will raise the temperature, so we're going to move in this direction. Then our temperature stops changing as we add heat. So we keep adding heat, and our solid melts to a liquid. So we stay at that same temperature, and we add a certain amount of heat. That's what's called the latent heat. For the case of the melting point, so this would be the temperature of the melting point, this latent heat is called heat of fusion. Then we're a liquid, and we, again, just have a linear relationship between Q and heat. That's just going to be the heat capacity equation. And then we hit the boiling point, and we have another latent heat, the heat of vaporization. And then after that, we're a gas, and we just continue to go upward. So in these angled slots, we are governed by the heat capacity equation. And in these slots, our temperature is not changing, and we have the latent heat there. All right, well, let's look at the special case of gas-liquid equilibria, and we're going to derive a related equation to the Clapeyron equation, the Clausius-Clapeyron equation. So, liquid to gas, and we'll set it up this way, so it's liquid to gas, so this will be evaporation this way, condensation this way. We're going to be at equilibrium. So at equilibrium, our delta G is 0. But delta G also equals delta H minus T delta S. So that means T delta S is delta H at equilibrium. And so we'll divide by T, and our entropy of vaporization is equal to our heat of vaporization divided by T. So let's substitute that into the Clapeyron equation. So let's grab the Clapeyron equation. Oops, this should be a big T, capital T. And we'll now substitute in for S delta H vaporization over T times delta V molar volume. Well, let's take a closer look at this delta V. What is this? This is the product minus reactant. So molar volume of the gas minus molar volume of the liquid. And if you remember back a couple of lectures ago when we were talking about, well, in one of the kinetics problem, the collision problem where we talked about mean free path, and we've talked about this a couple of times now, where the gas has so much space in between at room temperature that a molecule has to go many, many, many times itself to get to a collision. If we condense this out, then that volume is much, much less. And so for all practical purposes, this is dominated by the gas volume. So we can say that the change in volume is equal to the gas itself. So that's a good approximation. Then we could say, well, at room conditions, the volume is given to us by the ideal gas law, which is right here. So this is just the ideal gas law. And then we can substitute that in here, and we get an expression for the slope of this line right here, slope of this curve anyway, it's not necessarily a line, that is of this form. Heat of vaporization times pressure over RT squared. And this is called the Clausius-Clapeyron equation. And this is useful, again, for liquid-gas equilibrium. All right, so this is kind of a whirlwind tour of phase equilibria. And again, this is a pretty advanced topic. So we just want to get our feet wet with it in this course. And then later in the curriculum, we'll come and probably have a whole course on just phase transitions. Very, very interesting topic and a critically important area of physical chemistry research throughout history, but really quite a bit of work done in the 70s and 1970s and 1980s in that regard. All right, so that is phase equilibrium.